Hello learners, my name is Geoffrey Omondi. I will be taking you through the topic vectors. Now, this is the first topic of vectors. You will do 2 topics of vector in secondary schools. So this is the last topic in Form 2, and then there will be another vector called Vector 2 in Form 3. Now, therefore, I will call this Vector 1. Now, for this class, we are going to do the following. 1, we are going to define the meaning of vectors. 2, we are going to look at the difference. We are going to look at the difference between scalar quantities and vector quantities and 3, we're going to look at equivalent vectors, and representation of vectors, So for this class, we are going to do 3 things. We'll get the meaning of vectors. By the end of this class, we should also be able to give difference between a scalar and a vector quantity. And at the same time, we're supposed to be able to say what are equivalent vectors and how can we represent vectors. So we will start with the first thing and look at the meaning of vectors. Now, when you talk of a vector quantity, we say that a vector quantity is called so because it has to possess 2 characteristics. A vector quantity has 1, magnitude, and 2, a vector quantity has direction. Now, some may be asking what a magnitude is. Magnitude normally refers to length. Magnitude refers to length. It can also be size. When you look at a quantity, what is its size? What is the length? For example, you can say 5 kilometers, 4 centimeters, 20 kilograms. So that has to be the magnitude, length, or the size. Now, direction is towards what particular place is this length moving. For instance, you can say that Mr. X traveled 20 kilometers from town A towards town B. Now, 20 kilometers in that case would be the magnitude, and from town A to town B, that would be the direction. So I want us to move ahead and look at difference between a scalar quantity and also what we call a vector quantity. Now, just as I've said before, a vector quantity can be shown in a Cartesian plane. So that is a Cartesian plane. You'll be talking of x-axis, and at the same time, you are talking of y-axis. Now, be keen to show this continuity by putting an arrow at the end so that it can show that these values could increase, they could continue. We can draw any length like that, and this length we give it a direction. We have just said that vectors have direction. Now, we can call that B, and at the same time call that place A. Now, this would be a vector quantity. It is a vector quantity because one, we can get the length. We know, for instance, that we can get the horizontal movement between these two places. Say this movement, if we were naming this, say here is 2 and here is 5. So we could say that our horizontal movement is 3 units. We could also get the vertical movement that way and say that the vertical displacement here is probably, we can call here 1 and here 6. So we could say it is 5. So we know the length because we know that from A, we've moved horizontally 3 units, and at the same time, we've moved vertically 5 units. Now, this is a vector quantity. Talking about scalar quantity, for example, you could draw this line that way, call this A, call it B. We can easily get the movement horizontally, which will be presented like that, say X units. Still, we can get the vertical movement, but we don't know the direction. We don't know whether we are moving from B to A or from A to B. So in this instance, we'll be talking of what we are calling a scalar quantity. Let me just give you another illustration very fast. Now, suppose you're given a piece of block. Move it on the ground, and you're supposed to move this piece of block to a new position on the ground. So this is the piece of block. We are moving it to a new position on the ground, say movement of 5 meters. Now, we know that we are moving our block from point A here to point B, and we are moving 5 meters towards right hand side. 5 meters toward right hand side. Now, we also know that this block could again be moved towards any direction. So in this case, what we can say is that because we are able to define that our block is moved from point A towards point B, and that is to our right hand side, we can say that we are giving a vector quantity that would result into what we call a vector quantity. Now, if we just say, for example, let me just illustrate it from this place. If we just say, for example, that our block was moved 5 meters, that would be our first information. And then we give a second information and say that our block was moved 5 meters towards our right hand side. Now, these pieces of information, the first information is telling us about block being moved 5 meters. The direction is not said at all. Now, in this instance, we would say that this is scalar quantity. In the second instance, we are told of magnitude, that is the length in which the block was moved, and at the same time we are given direction towards which the block was moved. So these two pieces of information will actually make us conclude that our second statement is actually talking about a vector quantity. Our second statement is actually talking about a vector quantity. So that is the difference, learners, between a scalar quantity and also a vector quantity. Now, I want us to move straight ahead and look at how can we represent vectors quantities. Now, vector quantity, to represent vector quantity, I'll rub here. Yes. So what we're saying is that when you want to present vectors, normally you'll use 2 capital letters, or you can use a 1 small letter. Let me illustrate. So this is a representation of vectors, representation of vectors, representation of vectors. Let me write that like that. And we are saying that you can represent a vector, say vector AB, in that direction. So you've used 2 capital letters to denote vector. In this case, you are trying to tell us that the length of this vector is between point A and point B, and the direction is from A towards B. For instance, you can draw that and say this is A, this is B. This is the length we are talking about. And then the direction is this way, so we will show with that arrow. So these vectors can be represented as vector AB, which we are showing here. You can, for instance, represent vector CB, in which instance it means we are having a line from C towards B, and that is the direction, showing us that this vector, the direction is from C to B. Now, there are situations where our vectors can be represented by a single small letter. Say, you can find a vector written as vector A. Now, normally in typing, you'll write A, but a bold A. But when we are writing using our pens, it is normally A with a wavy line just below. So this is read as vector A. This is read as vector B. A, this is read as vector A. We could also have vector B, B with a wavy line just below it. We could also have vector C, which is a C with a wavy line just below it. Now, we can get all this information and write it in what we call a Cartesian plane. We can get this information and write it in what we call a Cartesian plane. For instance, drawing a Cartesian plane, you can draw a Cartesian plane this way. So this will be y-axis. Always remember to show that your Cartesian plane is continuous by drawing that arrow. This is x-axis, that is x-axis. Now, from here, we can draw any vector that way and call here point A, call that place point B. Now, from this, we can give it direction, so that is a vector quantity. And we can now decide to give this vector. Now, giving this vector, you'll say that we want vector AB that way. So this is read as vector AB. Now, giving vector AB in this case, we'll be forced to know the coordinates of point A and also know the coordinates of point B. So I would very first have arbitrary points like that. Let's call this is 1, 2, 3, 4, 5, that way. We can also have arbitrary points 1, 2, 3, 4, 5, in which case we'll have 1, 2, 3, 4, 5. Now, using this, we can get the coordinates of A, which are normally given first of all by the x coordinate, followed by the y coordinates. So we will have 1 in this case and 1. So we have point A being 1, 1. Point B in this case would be x-axis. We would have 4 followed by, let me just write it here, 4 followed by the x, the y coordinate 3. So we have 2 points A and then we also have B. So we have A1, 1 and B4, 3. Now, working with this, we can get AB. And getting AB means we have to see by how many units has A been displaced or moved towards B. Now, in that case, we'll find that A is at 1 and B is at 4 when you look at the x-axis only. So this will tell us that the units between 1 and 4 is 3 units. So putting this, we can write vector AB as 3 units to show us how we have moved on the x-axis, and write the second part as, so we will check we've moved from 1 up to 3 on the y-axis. So we can show that 1 up to 3, that is difference in units of 2 units. So we can say that in y-axis, the movement from A to B was actually 2 units. So we can represent this vector and say that our vector AB is actually 3, 2. Now, normally when you are giving vectors, especially when you are using coordinates, make sure that you give both the x, this is the x units, and also make sure that you give the y units. So you check by what units have we moved from one point to another when you are considering the x values, and when you are considering the y values, by what units have we moved from one place to another. So basically this is how we present vectors. Told you that we can use capital letters and show direction when you are presenting vectors, and still you can use small letters and show direction. Now, to use small letters and show direction, for example, in this case, suppose we had another line starting from point 0, 0, which is the origin here. Say this line is represented by OD, that is the direction. Now, in this case, this is called a position vector because it starts from the origin or the center of the Cartesian plane. So normally we use the last letter, for example, OD, we are moving towards D. So D here is the last letter, O is the first one. We normally use this last letter to give that vector a name. For example, this vector would simply be called vector D. Normally when you're only using one letter, use a small letter. In a situation, for example, where you have another line, say, let me just rub here so that you're able to see it clearly. You have a Cartesian plane like that. You have x-axis. You also have y-axis. You can have another vector, say this. So this is point 0, 0. I've just told you that these are called position vectors because they start from the origin towards, say, point B. Now, B is the ending point here, and we are moving from A towards B. This vector is a position vector, and instead of writing OB, vector OB, which of course is still correct, we can simply write this vector as vector B with a small wavy line just below the small letter B. So that is how we can present vectors. That is how we can represent vectors. So having looked at how we can represent vectors, I would now like us to see when do we say that vectors are equivalent. So the next thing I want us to look at for this lesson is equivalent vectors. Let me just write here, equivalent vectors, equivalent vectors, equivalent vectors. So you can be given a number of vectors. I've told you how vectors are represented. For example, you can be given vector AB. You can be given, say, vector CD. You can be given, say, vector EF. And you can be asked to check whether these vectors are equivalent or not. Now, just to remind us, we said when we were starting that vectors actually have two characteristics that make them vector quantities. A vector, we said that must have what we call direction. And we also say that a vector must have the second thing, magnitude, or what we sometimes call size, or what we also call length. Now, two vectors are said to be equivalent if they are moving in the same direction and they have equivalent magnitude. So let me just note that for you. Say that two vectors are said to be equivalent if they, one, move in the same direction, and two, they have the same magnitude. So we can illustrate this further by checking an example of two vectors, which we can use to show us whether two vectors are equivalent or not. Now, suppose we have these two vectors. Suppose we have these two vectors. So this is vector AB, that is the direction. And we also have vector CD, that is the direction. Now, suppose we have these two vectors and we are told that the length AB is 2 centimeters, and we are also told that the length CD is 2 centimeters. And then we are told that these two vectors are parallel. We can write that as AB, these two lines are parallel, and CD. Now, this sign shows that AB is parallel to CD. So if we are told that they are parallel, meaning they are moving in similar direction, and we are also told that the length of AB, which is the magnitude of AB, is 2 centimeters, and the length of CD, which is the magnitude of CD, is also 2 centimeters, then we can say that vector AB is equal to vector CD. The reason is these two vectors have same length, which is 2 centimeters, and that length is magnitude. And at the same time, they are moving in a similar direction because they are parallel. So in that case, we are going to say that these two vectors are equivalent. Now, if we were to look at the same example and say that our direction of CD was the opposite, such that we now have a direction that way, we would say that vector AB in this case, would say that is not equivalent to CD. Now, this is the sign of not equivalent or not equal. We'll say that AB is not equivalent to CD. The reason is AB has a length of 2 centimeters, but moves in an opposite direction compared to CD. So because the directions are not similar, we say that the two vectors are not equal. We say that the two vectors are not equal. So learners, this information brings us to the end of our lesson today. In our lesson today, we've looked at the meaning of vectors, and we have said that vectors are quantities that have both direction and also what we call magnitude. We have said that magnitude can also be called length, and it can also be called size. In this lesson, again, we've looked at the difference between a vector quantity and a scalar quantity. And we've said that scalar quantities can have magnitude but lack direction, but a vector quantity normally has both magnitude and also direction. We further looked at representation of vectors, how we can represent vectors, and we've said that you can use two capital letters and show the direction of movement. And at the same time, you can use a small letter with a wavy line just below it. We've also looked lastly, but not least, the equivalent vectors. And we've said that two vectors are equivalent when these vectors have equal length and are moving in the same direction. Now, that brings us to the end of our lesson today. I hope we will meet next time in the next lesson. Thank you.